Topic C. Topic C, we'll be talking all about waves, but starting with C.1, we're going to talk about simple harmonic motions. And what are simple harmonic motions? Well, they're a type of motion that are characterized by consistent back and forth oscillation about an equilibrium position, where the object's acceleration is negatively proportional to its displacement. You need to remember this definition. It's quite important to define the properties of simple harmonic motion. This bit we can see in the formula later on. The equilibrium position can be seen as just the center, I guess, of the oscillation point. And in simple harmonic motion, it's going to oscillate from here to this maxima, well, back to the equilibrium position, onto this maxima, so on and so forth, back and forth oscillation. And the net force and thus the acceleration are always pointed towards the equilibrium position, always towards point B here. And we have an equation, A equals negative omega squared times x, where a is the acceleration, omega is the angular velocity, and x is the displacement. So as you can see here, acceleration is negatively proportional to the displacement. If you graph acceleration and displacement, then the slope of or gradient of the graph is going to be equal to angular velocity squared. And also you should remember the equations for period and frequency from circular motion, which are just period is equal to the reciprocal of frequency, vice versa, which can also equal to 2 pi over omega, the angular velocity. So there's two types of simple harmonic motion systems that you'll look at the IB physics syllabus, and those are the pendulum system, where here all the same concepts apply that I just taught, but you need to know a specific formula for the period and is in a simple pendulum system, which is the period equals 2 pi times the square root of L, which is the length of the pendulum here, this is equal to L, divided by g, the acceleration due to gravity, or 9.8 meters per second squared. So that's all you need to know for the pendulum system, besides this formula as well, A equals negative omega squared x. And likewise for a mass spring system, the other system that you'll look at, period is equal to 2 pi times square root of mass divided by spring constant k. And as you can see here, a key takeaway from this is, in a pendulum system, the period is not affected in any way by the mass of the object. Similarly, in a mass spring system, the period is independent of the spring length. It's only dependent on the mass and the spring constant, and here it's only dependent on the length and the acceleration due to gravity, which is a constant. And that's it for the SL bit component of simple harmonic motion. There's still more HL content to delve into further.